This is Science Max, Experiments at Large. Science Max!
Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large. Today, we're going to be looking at earthquakes. Earthquakes! Huh. Today, we're going to be looking at how to build something. That was supposed to happen earlier. Today, we're going to be looking at how to build something that stands up to the shaking of an earthquake. Earthquakes happen when two plates on the Earth's surface rub together, and it causes the ground to shake. It causes the ground to shake. Sometimes it shakes a little, sometimes it shakes a lot. Chances are you do not live in a place that has earthquakes. But if you do, ask an adult what to do during an earthquake so you can be safe. Modern buildings that are built in earthquake zones are designed to withstand the shaking. But how do scientists and engineers build a building that stands up to the shaking of an earthquake? Well, that's what we're going to be looking at today. First thing we have to do is simulate an earthquake. We're going to build a shaker table. And here's what you need. 2 books and... Two books, 4 elastic bands, and four rubber balls. Oh, wait. Okay. Four rubber balls. All right, so the first thing you do is actually take your 4 elastic bands and wrap them around your books. Put one set on one side, one set on the other side, till you have that. Then you take your 4 balls and you stick them in between the books in the middle-ish area. But you don't want to have them too close to the edges. And now 2 at the back. And ta-da! You've made your own shaker table. What are you shaking, you ask? I will show you. You build a tower. Like this one here that I built out of building blocks. So here's what you do.
You'll need your base to be securely attached to the shaker table. I use painter's tape because it'll come off again without harming the books.
And what I want to find out is just how much shaking this tower can take before it falls apart. Ready? Whoa. And there it goes. And when you've done that, what you do is you be a Science Maximite and you design another tower. And you tape it down to your shaker table and see if you can make this tower fall down in an earthquake. And if you built it really well, probably won't. But you don't have to just use building blocks. There's all kinds of other materials you can use. Check out this building, which is really tall, and you'll see there's a cup at the top, and that's for a baseball. Put it up at the top, and that means there's a weight up there. And then we shake it, and we see what happens. Oh no! Oh, there it goes. So that is what we're going to be doing today on Science Max Experiments at Large. We're going to be making a giant shaker table and putting a giant structure on top and seeing how we design it to make sure it stands up to the shaking of an earthquake. I'm going to need an expert to help me, though. Oh, I know. Anne would be really good at this. Okay, all I need to do is get Anne, and we can start. Oh, come on. There it is. All right.
Hey, Anne, I feel weird. Why do I feel weird?
I think you're a chair.
Well, that's not good. Hold on a second.
Am I good? Okay. Hi, Anne. Good to see you. Here's your lab coat.
Thank you.
So you're from Let's Talk Science, right?
I am.
All about science education, just like us. Today, I need your help to max out our earthquake table. This is the table
This looks
part,
great.
obviously, but this is a tower I've made out of popsicle sticks. So in order to max it out, I've already built a large shaker table. Come on. This is my large shaker table. So it's got basketballs underneath as the 4 balls, but it works exactly the same. Whoa. Whoa. Okay, so what kind of tower should we make for the shaker table?
If we want something tall, then we'll reinforce it a couple spots. But the true test, it's got to have some sort of weight on top so that it will mimic the weight that would be on a real tower.
Right, so maybe I could get a plastic bin and I'll just put some sandbags for weight inside.
That would be perfect.
And then balls, so that when it falls over, the balls will go everywhere.
That would be perfect.
Okay, great. Shake off. I don't know. I think we should just get off.
Another thing that happens during an earthquake is soil liquefaction. Liquefaction means something turns to liquid. In this case, the very ground you might be standing on. Here's how you can experiment with soil liquefaction. All you need is a plastic container and some water, not very much, barely enough to cover the bottom of the container, because what you're gonna put in next is sand. And you wanna put it in there and spread it around. Just add enough sand so it just starts to turn dry on the very last layer. So here is a house that I'm going to put on top. And now I will simulate an earthquake. The water rises up and it sort of turns to liquid. Soil liquefaction. And heavy things like houses and cars, they tend to sink like that. And then the soil rehardens and everybody's houses are stuck in the mud. Now, let's max it out. This is a giant tub of sand and water, and this is a vibrating platform that will simulate an earthquake. Now, as you can see, this sand is totally solid. I can jump all around on this sand, no problem. But when I turn on the vibrating table and simulate an earthquake, things will change. The vibrations bring the water below the sand to the surface and cause the sand particles to separate. What was solid now turns to liquid in my simulated earthquake, and I start to sink. I'm up to my shins! And there you go, soil liquefaction. Hey, look at that. It's totally solid. Woo-hoo-hoo! Soil liquefaction! I'm totally... Uh-oh. You know what I realized? When it stops vibrating, it really becomes solid again, and it's very tough to... Well, there you go. Soil liquefaction. I'm really kind of stuck in here. So Ann and I have made a large shaker table. Now it's just a matter of designing a building. We use lumber and cut it up, use screws to attach it all together, put a platform on top for a weight, and attach it securely to our shaker table. The building is super simple, just 4 corners and a few planks around the outside. No structure in the middle. And finally, the big heavy weight on the top. There. We attach a pole to the shaker table so we can shake from a safe distance and try it out. Okay, very slow.
Forward.
Let's see how much shaking it can stand with our shakeometer.
Good.
That seems to be okay.
Kidding.
Oh no. Oh no!
We barely start to shake our tower before it collapses.
Oh, that didn't really last very long, did it? It completely folded up on itself. What do we do to fix this, make it better?
I think the easiest thing we can do is to use thicker wood. It'll make it less wobbly.
Okay, sure, let's make another one. High fives. We do have lots of wood, that's a good thing.
Ann and I are trying small improvements every time.
There.
Our last building used thinner pieces of wood. Now we're using thicker wood, which we think will help keep the weight at the top from collapsing the building. Everything else about the design of our building is the same. We put the weight on top and fix our pole, and we're good to go.
All right, you ready?
Okay. Starting to creak.
But it recovers. You can see it lean, and then it comes back, and it resets.
Definitely doing better than the last one.
Oh, no. I'm impressed.
Uh-oh,
here we go.
It definitely did better than the first one.
It did better than the first one.
And the thicker wood definitely helped.
But it was really starting to turn.
I think on the next one, we need some platforms in the center to help strengthen it even more.
Earthquake Building 3.0. Thicker wood this time, but with platforms in the middle. so we're gonna see how well this version works with these middle parts that'll hopefully reinforce.
And they're just like the floors of a building.
Okay, well, let's find out if it's gonna make any difference.
Starting to wobble a little, but it looks pretty good.
As soon as we start shaking, it's really obvious this building is more solid.
Uh-oh, starting to creak. Oh, it's really starting to creak.
The platforms in the middle really seem to improve the structure. You can see it bend all the way over and still recover. But still, it wasn't long before...
Really starting to lean.
Wow, the extra pieces really kind of made it more impressive.
It definitely lasted a lot longer than the other two.
It did, but here's what I'm wondering. Are we going in the wrong direction?
What do you mean?
Well, because if it's really solid, it resists the change.
Okay, I see where you're going with this.
So if we make it flexible, it can resist the shaking of an earthquake.
I think it's worth a shot.
Yeah, okay, let's do it.
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. My tuna fish and meatball sub soup is coming along quite nicely. But what will we have for dessert? I know. How about earthquake buildings? Ha ha! It's a building made out of wafer cookies. But the people on Vanilla Street built in the gelatin neighborhood. And the people on Chocolate Street built in the crispy rice part of town. Exciting. Now, here comes the earthquake. Oh no! Oh, it's shaking! Oh, the shaking is come and gone for the people on Chocolate Avenue, and their building is still standing. Now, let's take a look over here on Vanilla Street, and here comes an earthquake. Oh no! Oh dear! Looks like the people on Vanilla Street are going to have to rebuild their building because it's all fallen over and being eaten. Delicious. Buildings can be built the same way, but the kind of soil they sit on make a large difference if there's an earthquake. Shaky, wiggly soil or solid, non-moving soil. So there you go, an experiment you can try at home. Delicious. Well, I'm Buster Beaker, and thank you for joining me on this episode of Cooking with Science. Now to try my soup.
Seismometer in 60 seconds!
Learning how to predict and measure earthquakes is an important branch of science. The Earth is shaking, but which way did the earthquake come from? It's all about measuring the vibrations, and to do that, you need a seismometer. All you need is a ball, some paper cups, some modeling clay, a pencil, and science tape, which is the same thing as invisible tape, except I use this tape for science. First, take your pencil and stick it straight down into the modeling clay. Then, you take your cups and you arrange them in a circle and tape the cups down. And that goes right in the middle, just like that. Now what you do is you take the ball and you carefully balance it on the pencil. Now you have created a seismometer. It will tell you what direction an earthquake came from. Watch, I will be the earthquake. Ready? Did you see that? The ball fell into the cup facing the direction that I hit the table. And now I'm gonna hit the table from over here. Yep, it fell in the direction that I hit the table. Okay, let's try from over here. There you go, your very own seismometer that you can use to measure earthquakes that you create on the table.
Back to our earthquake building. Ann and I tried a few different designs, and they each got a little better. But now we're wondering what would happen if we built the tower out of very flexible material. We used some plastic tubing and attached the wood with bungee cords, which are like big elastics.
Wow, okay, so looks good.
So let's test it.
Okay.
And sure enough, when we start shaking it, the tower holds up to as much shaking as we can give it.
Wait,
What?
aren't we missing something?
Oh, yeah, we're missing the weight at the top. Of course.
So I think we need to try it again.
So we add the weight to the top, and then everything changes.
Oh, no.
Look at it twist.
Oh, dear.
It's twisted. It's
A
gonna
flexible
go.
tower is great until you try to put a weight at the top. And then it just seems really unstable.
Oh!
Whoa! Look at that. It's totally bent.
It didn't break at all, it just fell over.
Yeah, it couldn't even support the weight.
So it was almost too flexible.
So I guess we should go back to a more rigid design. But what if we change the shape a little bit? 'Cause you know what I was thinking? This is a very stable shape. Triangle, because triangles are really strong. What about we make an X?
Like a triangle within a triangle.
Triangle, and then triangle. So that really reinforces all of the shaking, like all of the motion.
We'll never know until we try.
All right. Uh-oh. I have all my friends coming over, and I don't have a table. But that's okay. I will make a table using my friends. This is an awesome experiment you can do with 4 friends. Come on in, science friends. I've got Sam and Dylan and Polly here to help me. So everybody turn to your left and sit sideways on the chair, and then scooch the chairs into the middle. And then everybody leans back onto the knees of the other person. And then this is why I said you need 4 friends, because you need the 5th person to remove the chairs. Whoa. The reason why this works is because everybody's weight is being supported on the legs of the person next to them. Okay, we're gonna rotate in a circle, everybody. Okay, ready? Here we go, rotating, rotating. Oh, science table. Ooh, hey, we're pretty good at this. Okay, uh-oh. Oh no, oh no! So there you go. Awesome way to make a table using your friends. Well done, science. Here's an experiment you can do to impress the adults in your house. You need 3 glasses, all of equal height, and 3 knives, not sharp knives, the dull knives you use, maybe the ones you use at dinner time. Take your 3 knives and put them in a triangle, all equally spaced out. Then move the knives together to make a little triangle, right like that. Then what you want to do is you want to carefully arrange the knives so each knife is going above one knife and below another knife. So there we go. Then you want to take this careful pattern that you created and you want to put it on top of your 3 glasses. One where each handle of the knives are going to be. And if you place it carefully and you've done the over-unders correctly, it will stay up. Pretty amazing. The knives support their own weight. But they don't just support their own weight, they can support a lot more weight too. Pretty amazing, right? This is a great experiment. It's also something really interesting that we can max out. Come on. And here you go, the maxed out knife balance. I've got 3 pieces of lumber and 3 barrels, and as you can see, the pattern is exactly the same. Under, over, under, over, under, over. Ha-ha. So, the question is, how much faith do I have in science? It totally supports my weight. I know it's going to work because I know that a 2x4, which is the kind of lumber I'm using, can hold up my weight. So that means the structure can support me. Science! You know what the cool thing is? The cool thing is that even though it's holding me up, each one of these pieces of wood is only up because it's supported by the others. You pull one out and it all falls apart.
Ann and I have tried solid towers and flexible towers, and nothing has worked fantastically yet with a big weight on the top. Having a big weight on the top of our tower means we need something that will resist the movement of that weight. So now we're going to start with a triangle. Unlike a rectangle, triangles are very stable. A wider base keeps the structure from swaying too much. And cross braces in the middle mean that there are other triangles within our triangle, all the better to resist movement.
Thank you.
After Ann and I built our tower, we added the weight to the top, secured it to the base, and tried it out.
Okay, here we go.
Looking good.
No problem.
It's not twisting.
It's
Not leaning.
not even creaking.
No, it looks really good.
Wow, this one is really solid.
As you can see, this tower is way more solid than our square tower or the flexible tower.
Okay, look at that. Like, if that's not an earthquake, I don't know what is. Look at that. Look at the way the ground is moving.
I don't know if we can shake it much more than this.
Faster.
Our triangular tower is up past a level of shaking that made the other towers collapse. Now it's time to max out the shaking.
There's only one level of shaking that we can do above this.
What's that?
We shake from either side.
We give it all we have. The floor was bouncing from side to side, the tower was tilting, and was totally solid.
It's still holding strong.
In fact, Anne and I wore out before the building showed any signs of falling over.
I think we've done it.
Woo! Nice job.
Nice. Science Max experiments at large, earthquake-proof building. I mean, come on. That was impressive.
I like it.
Greetings, Science Maximites, and welcome to... Can you hear me? Greetings, Science Max! You can't... hold on a second.
Greetings, Science... Yeah, that's much better. Greetings, Science Maximites, and welcome to Science Max Experiments at Large. Today, we're going to be talking about sound. Sound is all around us. We use it every day, but what is it really? Sound is energy. Let's say that this is the... No, stay. Stay. Okay. That this spring is the sound of my voice. When I make noise, it travels away from me in a wave. One air molecule vibrates the next air molecule, vibrates the next, and it looks like a wave. And when there's a little bit of energy, the wave doesn't move very much. Science. But when there's a lot of energy, the wave moves a lot. Science! What do we do? What do we do to make sound louder? This is the Science Max theme song. But it's not very loud because the speaker on my phone isn't designed to make super loud noises. So what we're going to do is find ways to make the volume of that song as loud as possible. Here is one way. Take a phone playing some music and put it in a glass. Make sure the glass is empty, of course. Huh? And suddenly, it's a lot louder. Wow! Why this works is one of the things we're gonna be looking at today. So that's what we're gonna do today on Science Max Experiments at Large. We're gonna learn how to make sound louder, as loud as we can. But I'm gonna need an expert to help me. Oh, I know, Michaela from the Ontario Science Centre. She's very smart. All I need to do is go to the Ontario Science Centre and see if she's busy. Yeah, Michaela, it's good to see you.
Nice to see you too.
That was weird. I was wondering if you could give me a hand with an experiment.
Oh, I'd love to, yeah.
It's a sound experiment.
Sounds awesome.
Right on. Okay, we'll take the portal. We'll go back to Science Max headquarters.
Oh, take the portal? Cool.
Haven't you taken the portal before?
No, don't you remember? It wasn't working last time.
Oh, well, it's
Is it working?
fixed this time. Yeah, no, it'll be great. Trust me. Here we go.
Whoa. Phil, is everything okay?
Usually when I come through the portal, I land on something or something falls on me or...
Not today. It's your lucky day.
I guess so.
Safe landing.
Safe landing.
Nice.
High five. All right, so let's get started.
Okay, cool.
This is the experiment I want to max out today, Michaela. I know. Pretty impressive, right? No, hold on.
Okay.
So I take my phone and I play some music on my phone and it's louder, right?
Check it out. Phil, you've just made yourself a resonance chamber.
A resonance chamber.
A
Very
resonance
nice.
chamber is what we say when we're trying to describe how the sound is amplified. So if the sound's coming in from one direction, it's bouncing around, not really losing energy. So when more sound comes in, that's amplified. We hear it a lot louder.
That's cool. So that's what I want to do. Hold on, let me turn this up. That's what I want to do today. I want to max out as much sound as we can get out of the Science Max theme song, which
I'm
is
so excited.
totally awesome. So what else can we do to do that?
Well, there's a couple avenues I'm thinking. Do you want to try something with electricity or without electricity?
That's because with electricity, we're talking speaker systems and
Yeah.
Right. So why don't we do no electricity for now, and then we
Alright.
can jump to electricity when we feel we've exhausted everything that's non-electric.
Cool. So I was thinking we could try to make a megaphone, because if we have a lot of sound, we could, funnel it in one direction, and then it'd be louder.
Okay.
What do
Yeah.
you
So
think?
the megaphone's pretty easy to make, right? We could just use, in fact, we could use this piece of paper, right?
Yeah, let's try it. What do you think?
I think it's very megaphony. Science taping it up. Okay, ready? Okay, turn it on. Play it. And doesn't sound, but what if I do this?
Hey, there it is. Right on.
Oh,
That song.
yeah? You hear it?
Yeah. Oh, I hear it.
Okay. So that worked pretty well. So,
Oh, yeah, it works. Works well.
So this is pretty easy, right?
Yeah.
Megaphone?
Oh, yeah.
So why don't we max this out? Why don't we make a giant megaphone and see if it makes a big difference?
I think it will. Let's do it.
Sounds good. Let's get started. All sound is vibration, but it's really hard to learn about that vibration if you can't see it. I mean, sound is invisible, right? Well, here's a way that you can make sound visible. All you need is some plastic wrap and salt and a bowl, just a regular bowl, and an elastic, like this. So what you do is you take the plastic wrap and cut off a piece just large enough to fit over the bowl, and then use the elastic to wrap around the bowl to keep the plastic tight. Pour some salt on the bowl, and then watch this. Hello, vibrating salt. The plastic wrap is stretched tight over the bowl, making it like a drum. A drum that's very sensitive to sound vibrations. Your ear works the same way. That's why we call it an ear drum. The vibrations from my voice make the plastic wrap vibrate, and that makes the salt dance. But there's more. Let's max this out. This is a Chladni plate, and what it is just a piece of metal on a platform that vibrates up and down to a frequency which I can program with this dial here. And when the sound waves vibrate the plate, they can interact in ways that make the sand form interesting patterns. Take a look. The sounds I'm generating vibrate the plate, make it move like a wave. But when the vibrations reach the edge of the plate, they bounce back and interact with the other waves going the other way. The way these waves interact at different notes is what causes the sand to make these different shapes. So this is great, but you know what? We can max it out even more. Maxing it out even more. Okay, that's about as much as I can take of that. So Michaela and I are on a quest to make the loudest sound we can. The first step is to make things louder without using electricity. We've looked at a resonance chamber, and now we're going to make a large megaphone. Sounds can be amplified by bouncing sound waves around in a space. When I put my phone into the glass acts as a resonance chamber. The sound waves bounce around inside the glass, and they combine and stack on top of each other. This makes the sound louder. Resonance chambers are used by musical instruments, like an acoustic guitar. The wooden chamber bounces the sound waves around, and the sound waves build on each other to make the sound louder. A megaphone bounces sound waves as well. Instead of going off in all directions, a megaphone makes the sound waves all go in one direction. That's one of the reasons why a megaphone makes sounds louder, but only when it's pointed at you. So will a bigger megaphone work better? So we've made a larger megaphone, which is exactly the same thing. You just take a sheet and you roll it up, except our sheet was plexiglass covered in paper, and we've taped it together so it stays. And the idea here...
Oh yeah, bigger megaphone. We're gonna vibrate even more of the air inside of here, and hopefully this thing will be louder.
Okay, so you're ready to try it with the phone?
Yeah.
I think first we should try it with our voices, though.
Okay. Now, what's your favorite season?
Awesome, I can totally hear you. That's amazing. And it would be fall.
Oh,
No, summer. Spring?
Think
It's
about it.
anything but winter.
So the maxed out megaphone worked, but we still had to try it with my phone.
Okay.
Not bad.
Yeah?
Oh, yeah. Oh, definitely.
How about now?
No, not so much. Not so much. Oh, yeah. Nope. Nope.
So that is a
That was
great
cool.
example of non-electrical amplification.
That's right.
Amplified the sounds, no electricity. Okay, bye-bye.
Sweet.
All right.
Come on, make some noise! Well, how do you make noise? Well, to know that, you gotta know your sound. All sound is vibration. Here, take a closer look. You see? You got... Okay, let's try this again. All sound is vibration. The string of this guitar vibrates, which vibrates the air around it, causing the sound that you hear. Your vocal cords vibrate in your throat, causing you to make a sound. Ah, 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 la, 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 la. Look at this thing. Look at this thing. See how it's shaking back and forth? It's vibrating. Things that make a high sound, they vibrate faster. Vibrating really fast. Things that make a low sound, vibrate slowly. High note, vibrating fast. Fast! That's vibrating. And now you know your sound.
Everything has a resonance, a note that it vibrates best at. Let's say this fish tank is, well, any container where sound would be vibrating, and the waves of water are actually waves of sound. Now, normally, sound waves will bounce around inside the container, off the walls, and go back and forth like that. And how fast I move this piece of wood is the frequency, or the note, that we're playing. I could vibrate this wood very fast and make a high note. I could move this plank very slow and make a low note. And the waves just bounce around inside the container. But there's a speed I can move this plank where the waves stop going side to side and suddenly get twice as big.
The waves bouncing off the sides of the tank are meeting the waves going in the other direction. But what we end up seeing is peaks of the waves not moving side to side, just going up and down, like you see here.
This is the resonant frequency of this container. So, let's max this out. Say I have a wine glass, and I wet my finger and I rub it around the rim. It vibrates at a certain note. That note is the resonant frequency of this wine glass. So what would happen if we were to play that note back to this wine glass really, really loud?
And yes, this is something you should not try at home.
This note makes the glass vibrate the most.
Finding the perfect note things vibrate best at is great for musical instruments, but it's not great for this wine glass. The sound waves are causing the glass to vibrate a lot. And because this glass is delicate, it can only vibrate so much before it breaks.
The vibrations were so strong that the glass literally shook itself to pieces. Science! Sorry. Science! Oh, wait. Science!
Michaela and I have tried a resonance chamber and a giant megaphone to make sound louder. Now it's time to move on to the next step of the plan, using electricity to help us amplify sound. And that means speakers.
So
speakers that you have at home. 3 different speakers here, right?
Looks
3
really
different
busy.
cones.
Yeah, there's a lot going on.
So what's the deal?
Well, here at the bottom, we have a subwoofer.
Wait a minute, a subwoofer.
Subwoofer.
So it's a woofer, the word is woofer,
Yep.
and it's, okay, so it's for dogs, right?
No, a subwoofer is for low notes here in our speaker.
Ah.
At the top here, we have a tweeter.
So it's for birds. It's birds, dogs. So let me guess, low notes?
Yeah.
Tweeters, high notes?
High notes. And then we have this guy here in the middle, and that's called your mid-range speaker.
Oh, that's not nearly a cool name. Now we have speakers, we've taken a look at that, but why don't we take one apart,
Cool.
right?
Yeah, let's do it.
I've got this one here that I spilled juice on, so it doesn't work anymore. So I've kind of taken it apart. So
Cool.
it's got,
Oh, man, that's awesome.
okay, so it's got the cover. That's cool. So what I find interesting is there's the speaker and the wires, right? Because it's electrical amplification. But check this out. This is just a ring to hold that on. And the rest is just an empty box.
We know what that is. Resonance chamber.
That's right. So that's why it's an empty box. So
Let's take this apart too, see what's going on.
So that's the paper cone, right? So that's that's the drum, I guess. It's like the eardrum, the thing that vibrates.
Yes,
Yeah.
this whole thing vibrates.
So that this whole thing-
That's for electromagnet. When we turn this on, the electromagnet goes on and off, and it's causing this whole thing to vibrate.
So that's how it works. It's the electricity turning the electromagnet on and off.
Exactly.
And it's on and off and on and off and on and off and on and off. And then it makes it vibrate at certain speeds, right? Hertz. The number of times it vibrates per second is hertz. What we could do is we could max it out with the speaker and plug the phone into the speaker. But this step does not feel like Science Max to me because anybody can do that, right?
Yeah.
You can just turn up your television right now, and that's pretty much the same kind of thing. We need electrical amplification, but maxed out.
Max it out. What are you thinking?
Okay, so I've got a friend, and he's got a stereo system that he built, put together, and what he does is he tours different cities. So he said he'd bring it by Science Max headquarters.
He's gonna bring it here?
We gotta go outside.
We can see this thing.
And it's very loud, so we have to go outside.
When's he coming?
Right now. All right, let's go check it out. Seeing sound vibrations is fun. This kind of speaker is a special kind. It's called a subwoofer, which is designed to give you the low notes, the big rumbly bass sounds. I tilt the speaker so it's facing up and cover it with big sheets of plastic wrap, which I push into the cone. Then tape it so it's nice and secure. Then what you need is some cornstarch mud, which is 2 parts cornstarch, 1 part water. I've got some yellow cornstarch and some blue cornstarch. This experiment works the best with low notes. I'm playing a tone through the stereo that is very low. Here's what happens when I turn up the volume. It's alive! You see, cornstarch mud is a shear thickening fluid, which means when you impact it, it turns solid. So the vibrations from the speaker cone are making the cornstarch mud impact, and that's turning it into a solid. But then it sort of also melts back into a liquid, so you get little columns of cornstarch coming up and falling down again. It's like it's dancing. Whoa! Visual sound waves. Science! So Michaela and I are going to max out sound. To do that, we need a maxed out sound system. This is gonna be amazing. This
so
is gonna
cool.
be super maxed out sound experiment. This is
so
James,
pumped.
Michaela.
Hey, James, how are you?
Thanks for coming, buddy. Nice to meet you. So, tell us about your speaker system. It looks a lot like a vehicle.
This is my audio van. It's got 4 15-inch subwoofers in the back. It's got a whole bunch of power to power it, and I'm glad to be here to let you guys hear it today.
Wow.
So if I have a speaker at home, like a little speaker like this, how many watts do you think that would be?
Somewhere between 15 and 25.
15 and 25 watts.
Yes.
And you've got 4,000.
Yes.
So that's a lot more.
Yeah, quite a bit.
And subwoofers, they play low notes.
Yes.
So is that better when you have a van like this?
With a car audio van like this, you want to play low notes, like your house stereos, and that will play anything from 120 to 200 hertz. I'm playing 20 hertz to about 35 max for you guys today.
So that's like a sort of rumble of
Yes,
thunder,
very
kind
low.
of blah, 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 blah,
Yeah.
where you really feel it,
Yes.
like a train going past almost.
Oh, that's cool.
So we get our hearing protection on and we try it out. I know what you're thinking. Phil, what's the point of having loud music if you can't really hear it? Because we've gone from listening to music to feeling it. The sound waves are so strong that they have become a physical presence. Michaela's hair flies around because the air from the speakers is creating shock waves. The sound waves are so powerful, they move the air back and forth, which makes Michaela's hair dance all over the place. And my hair, not so much. I'm totally jealous of your long hair.
Yeah, you need to get longer hair.
Okay, hold on, I'll go right.
Okay.
Whoa! Science Mac, experiments at large, super sound! High fives. Okay, ready to go again?
So cool. Yeah, let's do it.
Okay, here we go.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max, we're going to be looking at gravity. What goes up must come down. Today, gravity is the force that makes things fall towards the ground. But just because it's a force of nature doesn't mean that we have to listen to it. No! Today on Science Max, Experiments at Large, we're going to use everything in the power of science to defy gravity. We are going to be making a hoop glider. Now, hoop gliders may not look like much, but they fly just like paper airplanes. Woohoo! And here's how you can make a hoop glider. Here's how you can make a hoop glider all your own. This is what you need. Index cards, scissors, straw, ruler, pencil, and of course, science tape, which is just like regular tape, except you use this kind of tape for science. So, here's how you do it. Take your index card and cut it into 3 equal lengths. Take 2 strips, and you take your science tape, and you tape those 2 strips and make a hoop out of it. And with the small strip, you want to make another hoop. Now, what you want to do is take your straw. Now, this straw has a little scoop at the end, and that's not very aerodynamic, so we're going to get rid of that. Ooh, maybe it was kind of aerodynamic. All right, now that we've got the straw, you have to align the hoop and the straw together. So here's what I like to do. Take some science tape and stick it on the straw, and then align it so that it's perfectly straight, and then stick it on. Looks straight to me, all right? The small hoop also has to be perfectly aligned with the first hoop. So again, put the tape on the straw first, then align them up, and then start looking down through it, make sure it's aligned. There. Once you have it all taped together, you're done, your hoop glider. And it flies just like a paper airplane. Pew! Awesome. So that's what we're gonna do today. We're gonna, oh yeah, I gotta clean that up. We are going to max out the hoop glider. I'm gonna go meet Sonia at the Ontario Science Center, and we are going to max out the hoop glider into a giant version. We'll probably have to change the materials we use because, I don't think we can get a straw that big or cardboard, but still, we can figure it out. All right, here I go. Aha!
Oh, hi, Phil. Yeah, what?
want me to help you with an experiment? Okay. All right.
Oh, Sonia, I came in.
Bill,
You came in here? I
Are
came
you
in.
okay? Are you okay?
Yeah, I'm fine. Come on, let me show you. This is what I would like to max out. It was in my pocket when I fell, so
What is that?
It's a hoop glider. It was a hoop glider. So how do we max this out?
First, we're gonna need a larger tube.
To
large
replace
tube.
the straw, yeah.
Exactly, and we're gonna need 2 hoops. So we need something that's flexible that will convert into a hoop.
Okay, that's great. So why don't we get started?
Sounds good.
All right, high fives.
You may recognize this. It is a spring. Yes, good for you. But did you know that springs can defy gravity?
Whoa! Defy.
Look at it fly!
Defying.
Okay, not exactly, but what if I was to hold the spring like this and let it go? What'll happen?
It'll fall. Yes, it'll fall. That is true.
But while it's falling, what happens to this end?
Does it stay in one place?
Does it go up or does it go down?
Let's find out. I'll bring this in so you can really see it. Okay, ready? Watch close. Did you see? Did you? No? Okay, tell you what. We'll watch it again, this time in slow motion. See? The bottom doesn't move, and here's why.
When the top of the spring is released, gravity and the tension of the spring are pulling on it. The bottom of the spring is being pulled down by gravity and up by the tension of the spring. These forces cancel out, stopping the bottom of the spring from falling until the top reaches it.
Until there's no more tension, and then the top passes the bottom, and the whole thing. That is how it works. But here is the real question.
Will it happen differently with a longer spring? Huh? Well, I just happen to have a longer spring!
Let's max it out! Bring it. Don't tangle it. So now that I'm up high on this fire escape, let's test it out. Okay, 3, 2, 1, go!
A longer spring still has the same forces working on it. The tension of the spring pulling it up and gravity pulling it down. No matter what size of spring, these forces cancel out for the bottom of the spring until the top meets up with it.
So there you go, an almost gravity-defying spring! Hey, there's no door handle on this door. I guess I have to take the stairs. Whoa.
Sonia and I are maxing out the hoop glider out of bigger and better materials.
This is the largest tube I have, right?
A giant ABS pipe and some bendable metal to make into hoops. Then we attach them all together and...
Okay, big hoop is done.
And little hoop is also done.
Awesome.
Not bad.
Not bad at all. Super solid.
And that's the thing. We have pretty heavy material, so it might not fly as well as we'd like.
But something heavy can always be good, right?
Oh no.
That's what I'm talking about. See how solid it is?
Pretty
No
solid.
damage whatsoever. You want to test it?
I think we should.
Okay. I'm excited.
we take our plastic and metal hoop glider outside to test it and...
Ready?
Ready?
1, 2, 3!
Huh.
It didn't really fly, did it?
Sonia and I made a very solid design, but the problem with it became pretty obvious.
Yeah.
It's just too heavy.
Well, that's what science is. Back to the drawing board.
Here's something fun you can do if you ever get your hands on a helium balloon. Now, helium balloons float up, not because they defy gravity, but because they're lighter than air. It's because the heavier air around it actually falls past the balloon, and that ends up pushing the balloon up. But what if this helium balloon wasn't lighter than air or heavier than air? It was exactly the same. This is what I like to do. Just take a helium balloon with a long ribbon and a bunch of paper clips, and adding a little bit of weight every time. And what we want to do is make this balloon neutrally buoyant. That means it won't go up or down, but it will be neutral. You want to check it every once in a while. Let's see, 3 paper clips is clearly not enough. 5 paper clips is, 5 paper clips is pretty close. It still might float down, so you want to take off just a little bit of weight, maybe about there. Watch this. You just take the balloon and you put it somewhere and it stays. It stays put. It doesn't go up. It doesn't go down. It's attached to nothing. Now, let's max it out. I had a big balloon and it was there. A giant balloon. And look, it's a great paper towel delivery device. Say, did you want some paper towel? Here you go. Science. Yeah, don't worry about Ramona. Just put them up high. Put them up, yeah, higher. Good. Hey. Grab it. Grab it. Gravity makes things fall. But where do they fall? They fall down. Towards the center of the Earth. Eh? Gravity. It fell, didn't it? So, the Earth causes gravity, right? Well, yes. Gravity. Oh, come on. Everything that has mass has gravity. Gravity. But the Earth has so much mass that the gravity produced by everything else is like nothing. I mean, forget about it. But let's say I was in space with this chicken. I would have gravity, and I could exert a gravitational force on this chicken. And if I get my angles right, I might be able to get the chicken to orbit me, like a moon. Behold, my chicken moon. Huh? Gravity. But let's get serious. What causes gravity? We don't know. What we do know is that without gravity, there would be no universe as we know it. No you, no me, no chicken moon. I'd miss my chicken moon. Chicken moon, you what? Gravity. Like it or not, the universe wouldn't exist without it. You like the sign? I'll give you a good deal. Half off. Back to our hoop glider, which was too heavy. Here's what I don't get. This is heavy, but I can still pick it up and throw it.
Yeah.
An airplane is way heavier. I could never pick up an airplane, but that can fly.
And that's because airplanes have engines, so it has a constant source of thrust. When we throw it, we just have an initial source of thrust. So we're throwing it, eventually loses its energy, therefore,
It falls to the ground. I see.
so we need something that's light, and something that's strong.
And strong. Okay, well, let's see what we can find.
All right.
Sonia and I try a plastic tube and some heavy-duty paper. We make hoops and attach them with some duct tape and run outside to try it out. Hoop glider dance! Okay, 3, 2, 1.
That's pretty good!
That was amazing! Let's try that again.
Here we go.
I throw the hoop glider, and although it doesn't keep flying forever, it goes much further than our first version, and also further than I could have just thrown the pipe by itself.
Pretty good!
So we've done a good job of making something that flies. Why don't we make a couple different kinds out of different materials, and we'll see if we can get one that flies even better than this.
I think that's a good idea.
Yeah, okay, let's do it.
Sonia and I have created a pretty good maxed out hoop glider, but we wanted to see if different materials would make an even better one. Sonia made a much lighter version,
This time I used cardboard.
and I
made this!
made a slightly heavier one.
Let's do it.
Okay, 3, 2, 1, go! Not bad. My turn.
Here we go.
Okay. That didn't really go very far at all, did it?
No.
Okay, so now we can measure it against the one that we threw before.
And
to see,
that went pretty far.
This went pretty far to see if we've got a better design here.
Here we go.
Right?
Awesome.
So, heavy one, no. Light one, no. Interesting.
No.
This design seems to be the best one. I keep thinking about how you were talking about thrust.
Yep.
All the thrust that we can put in is just what we can put in with one throw.
Yeah.
What if we could give it more thrust than that?
How can we do that?
I don't know, like some sort of slingshot or something. Like it'd have to be a pretty big slingshot.
A pretty big slingshot.
Do you
But
think
I
we can
think
make
that sounds great, though.
I think make a big slingshot for this?
Why not?
Okay, high five. Let's do it. This is an egg. Eggs do not like to be dropped. Oh, fortunately, we can use the power of science to design something that'll keep the egg safe as it falls. Behold, my egg drop contraptions. The thing I really like about this experiment is there's no wrong way to do this. You can come up with any design you want and see if it works. This one here is a bunch of helium balloons. This structure is just to keep the helium balloons on so the egg can touch down very gently. Here it goes. Whoa. and the egg is unharmed, miraculously sound. That one worked really well. Success. This is a giant helium balloon that I think will work pretty much the same way because I think this balloon will drop just slowly enough that the egg can actually just touch and nothing will happen. So that didn't work. And then there's this one, which has no slowing at all. It's all designed to just absorb the impact. And the idea is that the cone will crumple and absorb the force when it hits the bottom. Oh, no! Oh, no. I think it would have worked if it hadn't turned in the air, but it did, and, well, I guess the egg is completely broken. So I'd call that one a fail. This one is the parachute. You see the egg has been nestled into this foam container, and this is a parachute that will hopefully slow the egg down. Woo! Uh-oh. Whoa. Over. Good. And that one seemed to work well. Yep, the egg is totally fine. The parachute worked. All right, egg drop experiment, totally fun experiment to do, but the question is, how do we max it out? And the answer is pumpkin drop. Same thing, except with a pumpkin instead of an egg. Come on. Okay. All right, pumpkin drop with everything attached all at once. Okay, here we go. Ready? 1, 2, 3. So what we've learned from this is the heavier something is, the more force is acting on it from gravity, which means the harder it is to slow down when it's falling. Okay, fair enough. You win this one, gravity, but I'll beat you next time. I'm gonna get a broom.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. Delicious. Nothing is more important to have fresh than your seafood. It's what makes the difference between a fresh fish and one that isn't so fresh. If you live by the ocean, you probably know that the water gets high tide and low tide.
Look closely, it's the same location.
Amazing! But did you know that this is caused by the gravity of the moon and the sun? See, this cookie is the Earth. And this little happy fellow is me. Hello! And this string represents the water around the Earth. If we didn't have gravity to worry about, the water would all be equally deep around the Earth. But here comes the moon, this mushroom. Now, the moon has gravity, and that pulls the oceans towards it a little bit, like this. And that creates high tide there, and low tide here, and a little bump of high tide on the other side of the Earth. And as the Earth rotates and I'm on it, I experience low tide and high tide, and low tide and high tide. Very interesting. But there's another factor. The sun, or this lemon. Now, the sun also affects the tides, but not as much as the moon. Now, the sun does not affect the tides as much as the moon because it's much further away, but it still has an effect. If the sun was here, then the tides would be pulled away a little bit like that, and the tides would be less severe. But if the moon and the sun line up, like over here, you'd get a very, very high tide and very, very low tide. So there you are. That's how the tides are affected by the gravity of the moon and the sun. Delicious. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
Our maxed out hoop glider was working pretty well.
That was
Pretty
amazing.
good. Here we go.
But we could only give it so much thrust by throwing it. So we came up with the perfect Science Max solution.
Our giant slingshot!
We pull the bungee cord back and hook it onto our hoop glider.
I am ready to fire. Count me down.
3, 2, launch it! Very nice!
Our slingshot is amazing. By giving the glider more thrust, that is, more energy at the beginning so it's going faster when we launch it, the glider soars through the air and flies a long way.
That was great! So there you go. Giant hoop glider. Yeah! Science Max. Experiments at large. Nicely done.
Nice.
What more could you ask for?
Well, my turn.
Hey, see you next time. Greetings, Science Maximites. Take a moment and imagine with me, if you will, a time when the only way to light your house was with candles or oil lamps. There was no electricity. That meant no power tools, no video games, no telephones, and worst of all, no TV. Fortunately, we live in a world of electricity. If you've ever lost power in your city or neighborhood, you know how hard it is to get by without electricity, even for one day. But where does it all come from? Where do we get this electricity that we use all the time? We make it. That's the cool thing. And I can show you how to make it as well. Check it out. All you need is an electric motor. Electric motors are pretty simple. All you do is get a battery and you attach it to the electric motor, and that makes it work. There we go. Attached to the battery, it spins. But if you spin the electric motor, it creates electricity. And that's what we're gonna look at today, creating electricity. We're gonna build a wind turbine. But first, you need an electric motor. And you can probably get one from a broken toy. Just make sure that the toy is broken and that the broken part isn't the electric motor.
Here's what you need: index cards or construction paper, scissors, push pins, science tape,
It's the same as invisible tape, except I use this one for science.
a cork, chopsticks, craft sticks, and modeling clay. And remember, all the steps for this experiment are on our website. To begin, cut the index cards into strips and tape down a push pin so it sticks out. Then fold over the index card and tape it together. Then stick the pin into the cork and repeat that step.
If you want as many blades as you can get on your fan, you're welcome to do that.
Next, take your modeling clay and stick the chopsticks in, then tape the craft sticks in between with science tape. Then take the motor and stick the cork on the end, then wedge the motor in between the craft sticks and tape it down so it stays put.
And there you go, a fan that will spin in the wind.
You want to adjust the fan blades so they all face on a bit of an angle. That way they will catch the wind and spin.
There we go. Now, when it spins, it will create electricity. I'll show you with this. It's a multimeter. And a multimeter measures little amounts of electric current. There. The hairdryer makes wind, spinning the fan blades, and we are creating electricity. Now, pretty much all electricity that you make comes down to turning a generator. A small motor like this isn't gonna produce a lot of electricity, barely enough to power one tiny little LED, but it's a start.
And a good start is all we need, because
Today, on Science Max Experiments at Large, we're gonna look at all kinds of different ways of generating electricity. Plus, I wanna find out just how much electricity one human being can generate. Although one human being is gonna be kinda lonely, I'm gonna need an expert. Oh, I know, Anthony from the Ontario Science Centre. He can help. I wonder if he's busy. Well, come on. Oh, Anthony! Phil? So I was wondering if you could help me with an experiment. I want to generate as much electricity with human power. What do you think?
I think that sounds awesome.
Okay, great. Let's go back to Science Max headquarters.
Is that the portal?
Yeah. Don't worry, all the kinks are worked out. I know what it is. It's this. Where did you end up?
I was in the vents.
oh, I ended up in the bathroom. All right, well, now that we're here, okay, so this is what I started with. And this is just, you know, an electric motor, right?
Right.
So you can generate electricity, you spin it, so I figured in order to generate more electricity, you get a bigger generator?
Exactly, yeah. The bigger the generator, the bigger the magnet, the more the copper, the more the electricity.
Oh, well, you know what we should do is we should just get an even bigger one, like a giant one that they use in like at a power plant or something, or?
Not quite. That would be too big for a person to be able to turn. It'd just be impossible.
So do you think this is a good size?
I think this is great size.
Okay, so that's good.
This is called a multimeter. We're gonna hook up the wires. I will do black to black.
Black to black.
The red. And as you turn our generator, we can see just how much electricity we're generating. Okay, so.
Here, you hold on to that.
This,
and
and you
I'll
can
turn
start
the
turning it.
generator.
Now it's time to play How Much Electricity Did They Make?
2.4 volts, yeah, it's not bad.
Oh, 2.4, yeah, it's not great.
That's just enough to power a small LED flashlight. Better keep trying, boys.
I got some handles here that we're going to attach
that
to
would be
the
perfect.
end of the generator so
Yeah.
we can spin it.
Okay, let's try.
No matter how fast I cranked the large handle, I couldn't make any more electricity than before.
Okay, let's try something else.
But it's a smaller handle.
Perfect, okay, yeah.
That's good?
Yeah, well, maybe it'll let us get more spins in.
Oh, yeah, because I don't have to make as big a circle.
Exactly. Yeah, it's working already. We're up to like 3.5,
Now how much electricity is Phil making?
4.5.
That's the same as 3 AA batteries. Maybe enough to power a toy car. Still a long way to go.
Yeah, it's a lot higher with the faster spins. Oh, all right. You okay?
I'm okay.
Maybe we could use like some gears or something like that.
Oh, yes, you know, that's a good idea because this circle that I'm making here, I can only go so fast. So
Yeah.
maybe with gears, you can do 1 circle here equals like 10 circles on the other gear.
Exactly.
Yeah.
Okay, so kind of like the gears on like a bike.
Yeah, the gears on a bike or something like that. A bike! Of course! Yeah, so we get a bike and we attach the back tire to the generator.
The generator, and then you can use the pedals of the big gear to power the small gears.
Okay, great. We'll go get a bike.
Yeah.
Yeah, high five. All right. Oh, right, they're over here. This is a generator. It generates electricity when you spin it. But how does it work? What wizardry is inside? Well, actually, generating an electric current is fairly simple. All you need is 2 things. First, you need a conductor, like this coil of copper wire, and you need a magnet. Now, this is a galvanometer. It measures small amounts of electric current, and I have my copper wire attached to it. Watch as I put the magnet inside the copper. I get a little bit of an electric current, and then I take it out,
it goes in the other direction. A little bit going this way, and then I take it out, a little bit going that way. Positive, negative, positive, negative. This kind of current that goes back and forth is called alternating current, or AC. It's the same kind of electricity you have in your house. But here's the cool thing. Watch this. I put the magnet in and I leave it. It goes back to zero. You only get electricity when you move the magnet. All right, so let's create our generator. Instead of starting with a copper coil like this, what if we just had the magnet and we have it staying still, like that, and we move the conductor past it, like spinning? It's good, but not great, because we're only getting a little bit of electricity as it passes. So let's make it more efficient. Let's put in some more magnets. One on either side, and one on the top. And now when we spin it, it goes past all of these magnets, and every time we get a little bit of electric current. Well, this is how a generator works. If you take an electric motor or a generator apart, you can see there's a coil of copper wires on the shaft, and it spins around like this. And on the inside, there are magnets. So there you go. When you put it together and spin it, you get an electric current. Or if you put an electric current in it, it will spin, just like an electric motor. And that is how a generator works.
Anthony and I are trying to create as much electricity as we can using just human power. But so far, it hasn't been going so well. It all comes down to how fast we can spin the generator.
Maybe we could use like some gears or something like that.
In order to get it spinning really fast, we're gonna use a bike. It's just a matter of getting a bike, taking off the wheel, putting it on a stand,
It is now a stationary bike. It'll be even more stationary once we screw it down.
and attaching the generator.
All right, the bike generator. Bike-orator, what should we call this thing?
Bike-nator.
Bike-nomator. I like it. So, okay, let's go over what we've got here.
Okay, so we've got 2 gears. We've got a big one, we got a small one. We turn our pedals, and the big gear turns the small one.
So this is the whole point of this build, is so that we can get one revolution here means a whole bunch is spinning there.
Exactly. The more we get here, the more our generator spins, and the more electricity we get. We get tons.
Awesome. And obviously using bike, because you're using your legs.
The strongest muscles in your body.
Awesome. Okay, so now what's with this horn? That is a loud horn.
I know. I tried to warn you.
That is great. I love that.
So Anthony and I hop on and give it a pedal. We pedal as hard as we can, and we produce a pretty good amount of electricity. How much electricity did they produce?
We got up to maybe like 18 there. You did a pretty good job.
That's enough for a power tool, like a drill.
It's good. You know what? This works well, I think, for keeping a good number for a long period of time.
Yeah.
So we can get up to like 18, 20, but it doesn't, we can't really get any higher than that.
Yeah, you know what we need is like one really hard pull, like all of a sudden. That way you can get like a spike.
Yeah, you're right. So it's like instead of putting all that effort into it going for a long time, you put all the effort into one quick motion.
Exactly.
Yeah, good idea. So you wrap a rope around here and then you just pull it.
Exactly.
And that'd be a really fast motion. Spin it really quick and get a very high number.
High spike, exactly.
Okay. You know, we're gonna have to take the bike apart though.
Okay,
All right. Well, it's science.
Okay, cool. So I'll just get.
Oh, you know what? We actually don't have to take the whole bike apart. We just have to take the generator off.
Oh, right. Okay.
Okay,
Hang
cool.
on a sec. I got it.
And maybe we should attach the horn to the next thing too.
Turn it off! It's so loud!
So you want to generate some electricity. But what do you choose to generate that electricity? Hydro? Nuclear? Coal? Solar? Who knows? I do. I know. And soon, so will you. In order to generate electricity, you need to turn the generator. Turn the generator. One of the most common ways to turn the generator is to use one of these. It's a steam engine. Usually they're a lot bigger. You see, you heat the water to boil it and turn it to steam, which works a piston, which turns the generator. Huh? Pretty amazing, right? But what it really boils down to is heating water to make steam. Boil water to make steam to turn the generator. Coal power. Burn the coal to boil water to make steam to turn the generator. Natural gas. That's different, right? Nope. Burn the gas to boil water to make steam to turn the generator. Nuclear power. That's different, right? Nope. It creates heat, which you use to boil water to make steam to turn the generator. Wind power. We don't even need heat for that. Just use the wind to spin the fan to turn the generator. Hydropower. Just pour water across something that spins to turn the generator. No matter what, making electricity always comes down to turning the generator. It's always yada yada, yada yada, turn the generator. Except for solar. Solar does not work like that. But other than that, it's always yada yada, yada yada to turn the generator. And now you know your electricity generation. Hey, Ramona, you wanna come and give me a hand over here? My arm is getting tired.
Whew, it is hot out here. Oh, in order to generate electricity, you need to spin a generator. Most forms of electricity generation work like that, but not solar. Solar panels like this one generate electricity from the sun's energy. So, how do they do it? Well, this is a solar panel. Okay, it's not really a solar panel, I just sort of put this together, but it works the same way. There are two plates, and on these plates are electrons. I've got golf ball electrons up here, ping pong ball electrons down here, but they're all the same thing. Now, this happy little fellow is a photon, energy from the sun in handy-dandy particle form. What happens is photons come from the sun and hit the top plate and knock some electrons from one side to the other, like this. And that knocks over some electrons. Now, these extra electrons travel up a wire in the form of electricity, and we can use them to do work for us. Then they change to the other charge, go back, and we start the process all over again. That is how solar panels work. But remember, it only works when there's sun and photons.
Anthony and I are trying to generate electricity using human power. Spinning the generator didn't work too well, but we found if we used some gears, like those on a bike, it worked better.
You know what we need is like one really hard pull, like all of a sudden.
Using gears is a great way to get work done. The good news is there are generators with gears already in them. That means if we can turn the spindle once, the gears inside will spin the coil a lot of times. The only downside, turning the spindle gets harder the higher the gear. Anthony and I attach a spindle, and then we wind up the rope, which takes a while.
Okay, so the plan is, it's on a big spool now.
Yeah.
And you just run as fast as you can.
Got it.
And we'll hopefully get as many revolutions as we can, depending on how fast your top speed is.
Okay.
Sounds good?
Sounds good. I can be pretty quick.
Okay, good. All right.
Ready?
On your mark.
Uh-huh.
Get set.
Uh-huh.
Go.
How much electricity did they create? 24 volts.
Actually, not bad.
That's enough to power their own personal scooter. Not too shabby, boys.
We need like a hard pull all at once.
Yeah, from something like really big. So what if we could get like really high, like up there? Could we attach the generator up there? You could jump down from there.
And I would hang on the rope?
Yeah.
Yeah, it's good, but I don't want to jump from up there. Oh, what if we put a pulley up there?
That
and
would
then
work.
the rope goes through the pulley and then back down, and then I jump from somewhere much safer, like just on top of here onto a crash mat or something.
That sounds great.
And that's my full body weight on the rope.
That sounds great.
All right, high fives.
Yeah.
Tidal power in 60 seconds.
By now you know that in order to create electricity, you need to spin a generator. Scientists and engineers are always coming up with lots of new ways to use natural forces of the Earth to spin a generator and create electricity. One of those natural forces One of those natural forces is the power of the tides. You see, the water in the oceans doesn't stay still. Every few hours, the water, or the tide, goes out. And then a few hours later, it comes back in. So if you attach a paddle wheel in the water and attach that to a generator, when the tide goes out, it creates electricity. When the tide comes back in, it creates electricity. That is how you create electricity using the power of the tides. It's water power. In fact, hydroelectricity is also using water power. Do we have time to talk about hydroelectric? We don't have time? We don't. Okay, maybe come back.
Hydroelectric power in 20 seconds.
20 seconds? Okay, hydroelectricity comes from water. Hydro means water. So all you have to do is find a place where water pours down from a height. And you can put a generator in there, and ta-da, you're creating electricity with the power of hydro. Ha 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 ha, I did it.
Anthony and I have pulled and pedaled, and now we're going to hang on to the rope and use our whole body weight to spin the generator as fast as possible.
Okay,
Okay.
crash mat. Let me test it out.
Looks good.
Yep, it's good for crashing. So I go up here? Okay, I go up here.
Climb on up. We'll get you the rope. Got your helmet for safety.
Helmet for safety, crash mat for safety. So we have the rope, and it goes up through that pulley, and then back down to our generator with a spindle on it. And as I fall, the spindle will turn.
Exactly.
And hopefully the speed of me falling and holding and yanking it down as hard as I can will be the biggest spike of electricity yet.
That's right. We'll be measuring it on our multimeter. here.
Okay,
Okay.
ready?
You ready?
Yeah.
Here we go. 3, 2, 1.
I jump down and my whole body weight pulls on the line.
Oh, that was awesome. That was like our biggest spike ever. That was amazing.
All right, high fives, biggest spike ever. Is it enough to power my house?
Nope.
How much electricity did Phil generate? Almost 30 volts. How much does he need to power his house? 120 volts. He's still off by quite a bit.
Well, we've learned something. Nuclear,
Wind,
hydro,
solar,
natural gas.
whole power.
It's all great ways to generate electricity.
Yeah.
And human power,
Not so much.
not as good. But human power is more fun.
Yeah, way more fun.
Yeah, so your turn?
Yes.
Okay.
Give me,
You
give
take
me.
the helmet and I'll take the multimeter.
Okay.
And then we'll go and we'll do it again. Okay. Wait, I gotta wind it up. Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. At this very moment, half the lab is being held together with the power of electromagnets. Magnet 1 turning off. Electromagnets are a really cool and powerful way to interact with the world. And when I say power, that's because you need power to make them work or not work. Magnetism is an invisible force that has to do with the magnetic fields created by magnets that lets them attract things that are metal or each other. But electromagnetism is a little different. You see, magnets are magnets all the time. It's because of what they're made out of. Electromagnets are only a magnet when you have an electric current going through them, which means you can turn them on or off. Today, we're gonna be building an electromagnet. Oh, that was the wrong switch. Anyway, like I was saying, today we're gonna be building an electromagnet.
You need a bunch of copper wire, a very large nail, or something metal to become your electromagnet, electrical tape, a battery, an on-off switch, wire strippers or a craft knife, and the help of an adult, and finally, something to magnetize, like these paper clips. And remember, all of the steps for this experiment are on the website. To begin, take the copper wire and start at the top of the nail. Leave a little bit of wire sticking out, then carefully start to wrap the wire around the nail. Don't go all the way to the end because you need some metal to turn into the magnet. Instead, when you want to start again, run the wire straight back to the top and start wrapping again in the same direction.
And keep wrapping and wrapping until you get to this. Now, I've used some electrical tape here, here, and here to hold it all together.
Using your wire strippers or a craft knife and the help of an adult, remove the plastic coating from the ends of the wires. Attach these wires to the wires from the on-off switch with electrical tape, or attach them directly to a battery if you don't have an on-off switch. And ta-da, you have an electromagnet with your on-off switch. All you need to do is take the things you're going to magnetize, turn your electromagnet on, and suddenly it becomes a magnet. Pretty amazing, ha 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 ha. And then you can magnetize to your heart's content. But when you're done, don't forget, you want to turn it off. So that's what we're gonna do today on Science Max, Experiments at Large. We're gonna max out the electromagnet. So, where's my lab coat? Oh, there it is. We're gonna see how big we can make an electromagnet. And when I say we, I mean me and an expert. Let's see. Oh, Heather from the Ontario Science Center. She knows her way around magnets. So let's see. Yeah. I wonder if she's busy. Well, let's find out. And after we're done, I'll need to come back and clean up the giant mess I made in the lab. Hi, Heather, how you doing?
Good to see you, Phil.
I was just wondering if you could help me with something. Are you busy?
No, I got time.
Okay, great, because I'm gonna make a giant electromagnet experiment and I need your help.
That sounds like a lot of fun.
Okay, great. Let's go back to Science Max headquarters.
Oh, via the portal?
Yeah, by the portal.
Oh, okay.
You sure? I
Yeah.
know you're hesitant, so I want to reassure you, nothing will go wrong.
Great, okay.
Okay. Oh, hey, we're here.
We're outside.
It's okay, it's
no,
okay. Don't worry about it.
No,
No,
I think
it's fine,
definitely.
it's fine.
You all right?
Yeah, I was supposed to come in over there, but I came in over here. Oh well. So today, Heather, I want to max out the electromagnet. Turn it on, and it's a magnet.
Pretty good.
And turn it off, and it stops being a magnet. I want to make this into a much bigger, maxed out version.
All right.
So what are some of the things we can do to do that?
Well, actually, if you have a larger battery, one that has a higher voltage, we can try that for sure.
Okay,
that
so
will help.
there are batteries that are 12 volts?
Yes.
We could try one of
give it
those?
a try,
I think
for
those
sure.
are like bigger, right?
Yeah, bigger, more powerful, absolutely. Now, that's one thing you could do. You can also increase the number of wraps of our coil here.
So how many times we wrap that wire?
Yes, we'll increase that magnetic field, making our magnet stronger.
And of course the nail, which is important because that's the thing that eventually becomes the magnet, right?
Right on, yes.
So what I thought we would do is we would start with a bigger nail.
Oh.
What, right? So larger battery,
Yes.
more voltage, and a lot more wraps of the wire.
Right on, and we have more space for that now, which is smart. Good job.
Great, okay, so we'll get to work.
Great.
Max Historica.
If you've ever seen a compass, you know that the needle points north. That's because a compass needle is a magnet and it points towards the Earth's magnetic North Pole. And I'm using this compass to try to get to the North Pole. But it isn't easy. In fact, scientists knew there was such a thing as the North Pole as far back as the 16th century, but no one was able to actually get there on foot until 1927. You'd think it wouldn't be that hard, right? I mean, the needle points you straight there. Just follow the needle, right? But now that I'm here, I realize it's really difficult. I mean, the wind is incredible and the snow is intense and it's so cold. My hands, yeah. So, okay, we're not really at the North Pole. We were just sort of recreating that. But still, I salute the brave explorers who tried to make it there in the name of science. And I got a sense of it because the wind from the fan and the fake snow was. Okay, everybody, let's pack it up. I mean, that was pretty good. I just didn't know about that other camera.
So, back to our main experiment, where Heather and I are building a larger electromagnet. An electromagnet works like this. When an electric current is traveling through a wire, it creates a magnetic field. If you wrap that wire around something ferromagnetic, that's something made out of a metal that is attracted to magnets, like an iron nail, then it becomes a magnet. You can make a magnet stronger by wrapping more wire, which gives more distance for the current to travel, increasing the magnetic field, and you can also increase the strength of the current. Heather and I start with a coil of 30 meters of wire and start wrapping. And wrapping. And wrapping.
There, the wire is now all done. And remember, if you're doing this at home, do not use a drill unless you have an adult to help you out, because drills can be very dangerous. This one goes at a very slow speed, so it was okay. But yes, definitely an adult supervised activity.
Then we attach another on-off switch and make some leads that connect to a 12-volt battery. So, more wraps of wire and more current means the electromagnet should be stronger.
Okay, so we're gonna try this electromagnet, and we're gonna pick up this stuff right here.
Great.
Ready?
You ready?
Yeah.
3,
2, 1, go! Is it on?
Yeah.
Wow, it really does, you can't tell it's on, but...
No, but bring it closer and...
Oh yeah, look at that. Okay, we turn it off.
All right.
Let's see if this nail can pick up this nail.
All right.
Ready?
Ready?
Go. Oh. Okay, how about this side? Oh, no. No.
I don't think we're strong enough.
It's not strong enough. I think that we need to max this out even more.
Even more?
Right.
So I'm thinking there are a lot of appliances that use electromagnets, meaning it's already set up, it already has tightly wound coils and high voltage. So we're in a lab here. Maybe do you have old appliances around?
I have parts bins with a whole bunch of stuff. Maybe we could find some electromagnets in those.
Let's do it.
Okay, great. Let's go. All right, pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need.
A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers.
So here's what you do. First thing is you put the batteries and the magnets together, like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here, and if you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So, now, let's max it out. Aha! A D-cell battery, which is larger and, of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and ha-ha! It spins! Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this. Huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil. I take the copper coil. I need to get. Okay, hold on. I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor.
Okay, so that didn't work. But that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement.
Heather and I built a larger electromagnet, but it still wasn't as powerful as we hoped. So now we're searching for parts that came out of an appliance that are pre-built electromagnets.
What about this?
I think that'll do the trick.
Do you think that does look like an electromagnet, huh?
It does, yeah.
And there's a whole big bunch of copper wires coiled on
Coiled
that.
around.
So you think we can use this?
Yeah, let's try it.
Okay, great.
We built the next version of the electromagnet. This one already has the copper coils, so it's just a matter of attaching wires and an on-off switch, and attaching all of it to a 12-volt battery.
Do you think 12 volts will be enough?
Let's find out. I think so.
Try that.
Once we do, it works much better.
Oh, no problem at all.
Ready?
Yep, turn it on.
On.
Whoa, pretty good. Okay, off.
Off.
Neat. In case it was really strong, I have the next step. Horseshoe. Okay, ready? Oh, whoa, that's...
Here.
I can't pull that off. Okay, wait, grab this. Okay?
Work together.
Yep. So that's passed all of our tests.
Yeah.
This is really strong.
Is there
What
a
do
way
we...
to test it further?
In order to test how strong our magnet is, it's as easy as seeing how much weight it'll lift. Heather and I find a metal table.
All right, Phil, so I brought the electromagnet.
Okay.
Just put it right here.
Yep. We add some sandbags for more weight and then attach a scale so we can measure how much weight we're lifting. We use a chain hoist, a simple machine made for lifting heavy things. This one can hold up to 454 kilograms.
Want to turn it on?
We're ready?
Yep.
Here we go.
You can read on the scale how much weight is being lifted.
And that scale is going up.
Pounds on this side, kilograms on this side. We keep lifting until...
Oh! Okay, so how much did it hold?
It held 100 kilograms.
Oh, that's more than I weigh, which gives me an idea. Come on.
This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this. Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out. This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet. And this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this. Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top. And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science.
The Wizard Academy. All you have to do is demonstrate true magic. And you will be granted entry. Well, Fuzzix, who is the next applicant for the Wizard Academy?
Overwhelmo.
Indeed, it is I, Overwhelmo. And prepare to be overwhelmed. Would you be flabbergastified if I balanced this coin on its end?
Not really, no.
But
Would you be impressed if I was to balance this coin on top of this coin?
Possibly.
Prepare to be flustered and stupefied. Stupeflustered as I balance 3 coins on their ends on top of this glass.
Well, that certainly would seem like magic. Let us see.
Okay. No pressure, Overwhelmo. You can do this.
And now, I say, a magic word.
A magic word! Ha 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 ha! And now you must let me into your academy.
Wait. What's under the cloth?
What cloth? This cloth? Nothing. Oh!
Is that a magnet?
This? No!
The pull of the magnet is what's keeping those coins up. The magnet is just strong enough to keep the coins from falling.
No, this is set dressing. It's just...
It was a good trick, but it's science, not magic.
Well, yes. And you will see! You will see! I will be back! I, Overwhelmo, will return! And I will do such magic that you will need extra socks. Because I will knock them off! With my magic, you will need at least 2 pairs of socks, maybe 3 pairs of socks.
We can still see you!
No, you can't!
So back to our main experiment. Heather and I have created a very strong electromagnet that can hold a lot of weight.
It held 100 kilograms.
Oh. Which gave me an idea.
All right, you ready?
Let's do it.
Electromagnets super maxed out experiment. We've got...
2 electromagnets, 1, 2.
And those are wired to 2 batteries, which are on my belt, just like this, so that I can carry them around. And we've got a crash mat here, because...
We need to keep you safe because you're going to be using these electromagnets to get across this massive beam above us.
That's right. I'm going to stick to this metal beam and go across with the electromagnets.
Wow.
We hope.
I have faith.
I'm glad you do. I've got a helmet for safety, goggles for safety, gloves for safety, but in this case, sometimes the lab coat is more safe and sometimes it's less safe. This time, it will get all caught up, so no lab coat. All right, you ready to go?
I'm ready. Let's do it.
Okay.
My goodness. 1.
Okay.
Because each of our electromagnets can hold more than my whole body weight, I can use them to cross the beam. When they're on, they stick like, well, magnets. And when I turn them off, they stop being magnets and I can move them along as I go. Now, this is something you should definitely not try at home.
Come on, Phil. You're almost there.
We did it! Yeah! There you go, Science Max, experiments at large, electromagnets! Woo! You wanna go?
No.
You sure?
I'm positive.
Okay, I'm going again. Woohoo!
Crazy.
This episode of Science Max is all about vibration and frequency. Frequency and vibration. What's the difference? We build a maxed out vibrobot, spin a giant disc, suspend water, and play with lasers. All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites, and welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max Experiments at Large, we're going to be looking at vibration. Vibration is when things go back and forth, and back and forth. All kinds of things vibrate, like pendulums. Pendulums. Wait, and pendulum. Pendulums are designed to swing back and forth. Stop that. Also, metronomes. Metronomes are used by people when they're practicing music to keep accurate time. Yeah. Okay, putting it back. And okay, we're gonna be building. Whoa, okay. We're gonna be building this little guy.
This is a vibrobot, and he vibrates and he skitters around on the paper. And if we take the caps off the markers, he makes interesting patterns on the paper. Okay, so let's get started. Let's build a vibrobot. Okay. Oh yeah, you know what? Maybe it's time to take off the ski boots, huh? Whew. There we go, that's better. So today, like I said, we're gonna be making a vibrobot. And here are all the materials you need to make your own. Plastic cup, 3 markers, an electric motor, just make sure you ask an adult first, a battery, a plastic drink bottle cap, a toothpick, scissors, this kind of tape is called electrical tape, science tape, which is the same as invisible tape, but of course I use this tape only for science, and some modeling clay. And these are 2 bendy straws that I've taped googly eyes to. These are not necessary, I just like them for decoration. Now remember, if I'm going too fast here, which I probably will be, you can get all of the steps on how to make your very own vibrobot on our website. Okay, so here's how you get started. First, you're gonna make the feet for your vibrobot. So I attach some science tape to the markers, and then I put the marker on the bottom of the cup. And then I do that again to the next marker, and then the third, balance it like that. There. Next thing you wanna do is take your plastic drink bottle cap and make a hole with a toothpick. You wanna make it off to the side, right about there. Just like that. That's so when it turns, it will be off center. That's what's gonna give us our vibration. So once you've made that hole, take some modeling clay and stick it in the cap to give it some weight. When you've done that, stick it onto the shaft of your motor like this. See how it's off center there? Now we just need to attach it to the vibrobot. I just put it right here on the top, and I like to attach the battery to the back of the cup. And now finally, we're going to attach the eyes. We take some science tape, and we put the straws over here. I am vibrobot. I am here to vibrate. Take me to your leader. So then you attach your tape with the wire to the top of the battery there, and then the other wire to the bottom of the battery, just like that, and let your vibrobot make some art. Ha 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 ha. Now, if the battery is new, your vibrobot might be jumping up and down quite a bit. So you can do what I like to do and add some more weight, and then you make better lines with your vibrobot. And your vibrobot makes art. How long will he last? Probably till lunch. And there you go, vibrobot art. Art made by a robot. How cool is that? So that's what we're gonna do today. I'm gonna meet Chris from Logix Academy, and he's gonna help me max out the vibrobot. Plus, we're gonna learn a little bit more about vibration. Come on. Oh, hey, Chris.
Oh, hey, Phil.
Thanks for coming.
My pleasure.
Okay, here's your Science Max lab coat.
Thank you.
So you guys at Logix Academy, you also build a vibrobot, right?
That's right, we do.
This is mine, and it works pretty well.
That's awesome.
So, I want to max this out.
Cool.
So I thought we would start with, instead of this motor, we would start with this motor.
Wow.
It used to be a round circle, but I cut it off so that it's off center.
Perfect.
I've also got, this is our battery.
Fantastic.
That's as far as I've gotten so far.
Well, it looks like we need a frame next.
Right, something to be the cup.
That's right.
So we just need some sort of larger cup.
Ooh, how about that metal shelf over there?
Oh, this thing?
Yeah.
This is just something I keep my parts on.
It's perfect.
Really?
Yep, the shelves will house everything that we need, and it looks like it'll be strong enough to hold everything together.
Now, the vibrobot had markers on the bottom of it.
That's right.
To make a little pattern. Should we try that with this?
Because we're going bigger, what if we used paint and paintbrushes instead?
Okay, sure. We could attach paintbrushes to the legs. Pass me one. All right, so now all we need to do is get some paint and some paper.
That's right.
And we can fire it up. Okay, let's move it over this way.
Vibration and frequency. What's the difference? They're all connected. Ta-da! Now, whoa.
Vibration is things going back and forth. Back and forth. And back and forth. It's a cycle. Cycle, $25. Oh yeah, it's the wrong kind of cycle. Never mind.
Well, if that's vibration, then what's frequency? Well, frequency is a measure of how fast or slow, how frequent those vibrations happen. Look at this bowling ball. Look. It is swinging back and forth, but not very fast. You could say it has a low frequency. We measure all kinds of things by their frequency. This thing is terrifying. When you turn the dial on your radio, you're tuning in to different frequencies of radio waves. Hey, look at this punching balloon. It's going very fast. You could say it has a high frequency. So, now you know. Vibration is something going back and forth, and frequency is how quickly it does it. Ramona, the bowling ball keeps coming through everything. How do you turn it off?
Okay, back to our main experiment. Chris and I are taking a vibrobot and maxing it out. We have a large motor and a battery, and we're taping it all to some shelving. Just like our small vibrobot, our motor needs something to make it unbalanced when it spins. That's what will cause the vibrations.
It's just taped. I haven't attached it in any other way. Do you think that's okay?
As an engineer, I have superior faith in duct tape.
Okay, well, that's good to know.
We're also adding an on-off switch and some paintbrushes on the bottoms of the legs so our maxed out vibrobot can make art just like the small one. The final step, dipping the brushes in paint and setting it on a big piece of paper. We fire it up and it immediately shakes everything off the shelves.
Oh! It totally spilled all the stuff on the shelves.
The motor shakes the vibrobot a lot. But there's a problem. All that shaking is starting to take its toll on the shelves. The wheels come off, the screws come out, and finally...
Whoa. It totally shook itself apart.
Destroyed itself.
The shelving unit just completely falls apart when it's being shaken.
Vibration is really hard on the structure of an object. We need something more sturdy, something that can take weight.
Steps, maybe?
Yeah.
Okay, hold on.
Okay.
Okay.
Yeah, this looks much better.
Okay, great. So we build the new vibrobot out of this. So more paint brushes.
Bigger motor, more paint.
More everything.
More everything.
All right, good.
This is a pendulum. It's just a weight suspended on a line and anchored from above. Pretty simple. Pendulums were used for hundreds of years for all kinds of reasons, but most famously in clocks. Why were pendulums used in clocks? Well, here's why. Let's mark every time the pendulum hits the bottom of the swing, right here. Okay, watch. All right, now here's the question. How fast will the beeps be if I swing it from much higher up? Let's find out.
No matter how high the pendulum swings, it keeps the same frequency. That's why they were used in clocks, because it could swing for a long while, and even though it would lose energy, it would still keep perfect time. The frequency of a pendulum doesn't change, no matter how high it swings or how much weight is on the bottom. The frequency comes from how long the line is.
Now this is a pendulum wave.
Because each bowling ball has a line that's a different length, they have a slightly different frequency. They start out swinging together, but soon they start to make interesting patterns. Remember, each pendulum is keeping its own perfect time, even if it's slowing down. It's only the length of the line that gives each pendulum a different frequency.
And now we're gonna max it out with well, I guess these are already bowling balls, so this is already pretty maxed out. I'm just gonna leave that there. These are balloons. This is a laser, and these are awesome laser safety glasses. Now, lasers are made of light, and light has a frequency. In fact, each color of light has a different frequency. This is a red laser. Check it out. Yeah, cool. This is also a very powerful laser. Oh, I can pop the blue balloon with the red laser because the blue absorbed the red light from the laser and then it heated up and the balloon popped. But here's the cool thing. I cannot pop a red balloon with a red laser because the red balloon reflects the red light from the red laser and I can't pop it. If I wanted to pop a balloon with a red laser, I need to use a darker balloon, one that absorbs the red light, like a black balloon. So there you go. Lasers, frequencies of light. I'm gonna keep this red balloon because it's always nice to have a balloon.
Chris and I are maxing out the vibrobot, but our last version shook itself apart. Now the plan is to start with something more solid and try again. We found some very solid steps and added an even bigger motor, an even bigger battery, and attached a half-circle wheel to make the vibrations when the motor spins. We add some paintbrushes and fire it up.
Here we go! Come on!
Go, vibrobot!
It wants to move.
Is it moving at all? So it's still not working. It's sort of getting caught in the paper and it's on the paintbrushes.
And the paintbrushes seem to be absorbing too much vibration, and then the paper's stopping it as well.
So why don't we remove the paintbrushes?
Yeah.
And we might as well remove the paper if we don't have any more paintbrushes.
Yes.
And we'll see what happens.
We'll see what happens.
Okay. No paintbrushes, no paper.
Okay.
Now let's try it. 3, 2, 1, go!
Yeah! Aha! It's moving. Not bad.
The shaking is good, but I don't know if the shaking is enough. So what do we do?
Well, we could add another battery.
Another battery which would give it more power?
That's right.
Okay, let's try that.
Okay.
Okay, so it wasn't working before,
No.
not enough power.
And now we've got a second battery here.
That's right. We've wired them up so that one power feeds into the other, so we've got twice as much juice as we do.
So it's just a matter of clipping this onto there.
That's right, but hold on.
Yeah, safety glasses, because now we don't know what's going to happen anymore. Ready?
3, 2, 1.
The extra battery makes a big difference. The new vibrobot shakes around and only shakes itself apart a little.
All right, that was amazing. Okay, so all we needed was more power.
That's right. I think it didn't have enough power to vibrate up and down, and that's why it wasn't moving every time it hit the ground.
So I think if we're gonna use this much power, I think we need to build it again.
Okay.
Build it even stronger and with a bigger motor.
Yeah?
And more power. And then maybe I ride it. You think we can build that?
Of course.
Of course. Okay, let's do it.
You want to see something cool?
I can make this water levitate, defy gravity using the power of science. You want to see? Behold! Gravity-defying water. I can even make the water go very slowly. Or I can make the water go back up into the hose. Or I can make the water completely stop. You know what's interesting? The water does not seem to be stopped for me. You see stopped water because you are looking at it through a TV camera. See? Real life, TV camera. Real life, TV camera. You see, movie cameras and TV cameras take a whole bunch of still photos and then run them together really, really fast. 24 times a second for our TV cameras. I have created a device that drops water at 24 times a second, and what happens is everything lines up. So it looks like the water drops aren't moving. But watch this. I grab the hose and it's fine. But I let it go, and the hose is vibrating back and forth at exactly the same time the camera shutter is going back and forth, and everything looks like it stopped. The power of frequency has defied gravity. Okay, so not really. It's kind of a camera trick, but I prefer to call it science. Here's a fun way to play with things going back and forth. This is Euler's disk, and it's designed to spin like this.
What's going on is friction and gravity are slowing that down and pulling it towards the Earth. Now, you don't need a fancy disc like this to do this at home. All you need is a pot lid. Check it out. When the pot lid spins, friction and gravity start to slow it down, which means each spin gets lower and lower, and the frequency gets higher and higher. But the difference between a pot lid and Euler's disc is Euler's disc is made to go for as long as possible. The heavy puck has a slightly rounded edge and sits on a glass surface that is slightly concave, like a bowl. All of this is designed to make Euler's disc last a really long time, which is quite a while. But eventually, friction and gravity pull the disc down, and finally, it stops. Pretty amazing, right? Well, wait till we max it out.
This is Trevor, head of the Science Max build team.
Hey.
Thanks for setting this up, Trevor. So what is this?
This is a giant side of a spool, big hydro spool.
Okay, so this is the largest disc that we could totally find, and we've got it all hooked up here. We lift it up, we spin it, and then you pull the thing and it will drop down and spin like a coin, because it's the only way we can do that with something this heavy.
Yeah.
Ready?
I'm ready.
Okay.
Trevor and I hoist it up and get it suspended above the ground. Then I start to wind it up.
Ready?
When it's going fast enough,
And go, Trevor!
Trevor pulls the release and it turns out a 200-kilogram spinning disc works exactly the same. As it spins and rolls, gravity and friction work on it, and the frequency speeds up as it gets closer to the ground until it stops.
Giant Euler's disc. Nicely done, Trevor.
That was awesome.
That was great. Let's do it again.
All right.
Our vibrobot was working well, so that means it's time to make it way bigger. We started with a big metal table and added a huge motor, one 20 times as powerful as the last one. Instead of batteries giving us 12 volts of power, we're going to use a plug, which is 10 times more power. We've added an off-center wheel for vibration, bolted the motor to the frame, and added a protective cage all around to prevent anything from flying off. It even has a seat for me to ride.
Okay.
Okay.
You ready?
Ready?
Here we
We
go.
fire it up and it's very shaky.
Oh, wow. Wow. That was really uncomfortable. It was like very bangy, even with the seat.
Yeah.
I'm gonna try standing on it.
All right.
When I try standing on it, the vibrobot lives up to its name. It vibrates all around the lab.
Oh, wow. My legs are numb to the knee.
I'm not surprised.
Vibrobot!
All right.
Yeah, that worked really well.
That was awesome.
I really can't feel my feet right now. And it held together, which is impressive.
That's right. The more power and the stronger structure paid off.
Yeah, the only thing I regret is not getting a chance to, wait a minute, come with me. Okay, so I achieved my dream of riding the vibrobot.
You did.
But we never got a chance to make art, so we've dipped a whole bunch of nuts and bolts and heavy things in paint.
Yep.
And now we're gonna turn on the vibrobot and see if we can make some art. Let's see how it looks.
Oh, wow.
Ta-da! Vibrobot art. Vibrobot has been a huge success, and we got some art to keep. High fives. Well done. Science Max, experiments at large. Who gets to keep the art?
Rock, paper, scissors.
Okay. 1, 2, 3. Okay, tie. 1, 2, 3. Tie. 1, 2, 3. 1, 2, 3. Wow. 1, 2, 3. Ah, tie. 1, 2, 3. Man,